Let's talk about how we can use an LU decomposition of a matrix to help us solve systems of equations. So first, let's suppose that we already have the LU decomposition like we do have in this first example here, where it asks us to solve 1022 times 1 negative 101 times xy equals 31, and we're going to solve for xy. So again, notice that the left matrix here is lower triangular, and the right matrix here is upper triangular. So that's where the LU decomposition part comes from, lower and upper triangular matrices. All right, so first notice that if we multiply these two matrices together first, if we were to group the second two matrices together and multiply, it would still have x's and y's in it. So let's just treat that result as variables. We have a 2 by 1 matrix. Let's just treat it as a single variable to start with and call it uv as the variable we're trying to solve for. So in that case, we would have the matrix 1022 times the vector uv equals 3, 1. So now notice that we've got this in a form that we can already solve the system, because the first row here gives us the equation u equals 3, or said it more explicitly, 1u plus 0v has to equal 3. So that tells us that u equals 3. The second row here, if we multiply out, you'd have 2u plus 2v equals 1. If we plug in 3 for u and solve for v, we should get negative 5 halves. So we can take out, if we know that if we put in the 3 negative 5 halves in for this piece, we would have a true statement. So now we'll use this inside piece and figure out when it's equal to 3 negative 5 halves, and that'll give us a solution to the system. So if we set the 1 negative 101 times xy equal to 3 negative 5 halves, then again we can solve this one pretty easily as well. We've got y equals negative 5 halves from the second row when we multiply out. The first row would give you x minus y equals 3. We plug in negative 5 halves for y, and we get x equals a half. So we can see the solution to the system then will be xy is equal to 1/2 negative 5 halves. And you can actually check that you plug that in and you get a true statement. If you multiply those three matrices together, you really will get 3, 1. So again, before we go to the next example, let's run through this process again. We've got a lower and an upper triangular matrix multiplied together times the xy we're trying to solve for is equal to 3, 1. Noticing that we multiply these two matrices together, we would still have variables in them. So we just treat them like it's a variable, as uv in this case, and then solve for the u and v first using the lower triangular matrix. We take that solution and then we say, okay, if I want the lower triangular times the 3 negative 5 halves in this case to be 3, 1, then those two matrices that we multiplied together, the second set we multiplied together, that should be equal to the 3 negative 5 halves, and then we solve from the xy from there. So it's a two-step process. First solve the lower triangular matrix system, and then solve the upper triangular matrix system. All right, so let's see if we can do this where the matrix isn't already in as an LU decomposition. Let me scroll to the next page here. So let's say we have the system 2, 8, negative 1, negative 1 times xy equals negative 2, 2, and we want to solve that system. So the first thing we want to do is write the matrix, the coefficient matrix, as a lower triangular times an upper triangular. Well, getting the upper triangular is just a matter of putting the matrix in row echelon form, and a lot of times we like to have that upper triangular matrix have 1s down the diagonal, so we'll do that as well. So to put that in row echelon form, first we'll multiply the row 1 by a half and replace row 1. That gives us the 1, 4 for the first row. Then notice that we need to get a negative 1 below that 1 in the upper left-hand corner, so we need to add row 1 to row 2. When we do that, we get a 3 in the lower right corner. We need that to be a 1, so we do 1/3 row 2 replace row 2. Now these are the row operations that we use to put the matrix in row echelon form, and the row echelon form is going to be the upper triangular matrix we use. So we'll set U equal to 1, 4, 0, 1. To figure out the lower triangular matrix, well, remember that we can realize each of these row operations as elementary matrices and then multiply on the left. So if I take 2, 8, -1, -1, multiply on the left by 1 half 0, 0, 1, and then multiply that on the left by 1, 0, 1, 1, and multiply that on the left by 1, 0, 0, 1/3, the elementary matrices that give you those row operations, we should get this matrix. We want, when we take our lower triangular times this matrix, we want to get back to this. So to solve for this matrix, I need to invert all of those, move it to the other side, much like we do when we write a matrix as a product of elementary matrices. So we want to undo all of these row operations. So we'll do them in the order they appear, really, but we're going to do the inverses. So the inverse of this one would be multiplying row 1 by 2. The inverse of this one would be taking -1 row 1 added to row 2. The inverse of this one would be multiplying row 2 by 3. So that's where we get our lower triangular matrix. We're doing the inverse of the first row operation, the inverse of the second row operation, the inverse of the third row operation, and multiply the 3 together to give us 2, 0, -1, 3. So our lower triangular matrix is 2, 0, -1, 3. Our upper triangular matrix is 1, 4, 0, 1. And if you go through and check, if you take L and multiply it by U, you really will get that original matrix. So now like we did in the previous one, we're going to, if we think of this as being U times XY as a single set of variables, we'll first solve the lower triangular system. So we'll solve 2, 0, -1, 3 times a UV equals -2, 2. That gives us the equation 2u equals -2 from the first row, or u equals -1. The second row gives us -u plus 3v equals 2. Solve for v, we should get 1/3. So now we solve the upper triangular system using the solution we just came up with. So we solve 1, 4, 0, 1 times xy equals -1, 1/3. The second row gives you y equals 1/3. The first row gives you x plus 4y equals -1. And then if we solve for x, we'll get x is -7/3. So we can check that the solution of the system is -7/3, 1/3. So again, before we do the next example, let's recap what we did. We started with our coefficient matrix. We put it in row echelon form. The row echelon form that we got is the upper triangular matrix that we'll use as our part of the LU decomposition. To get our lower triangular, we run through our row operations that we used to put the matrix in row echelon form, and we use the inverse of those. So we will do 2 row 1 and replace row 1. That's where the first one came from. Likewise with the second, we did negative row 1 added to row 2 to undo it. Here we had 3 row 2 replace row 2. So that gives us our lower triangular matrix. We then solve the lower triangular matrix system, and then solve the upper triangular system. Okay. Let's do one more example, a little bit bigger. We'll do a 3 by 3 system. If I can get to it, here we go. So we've got the system -3, 12, -6, 1, -2, 2, 0, 1, 1, times the variables x1, x2, x3 equals -33, 7, -1. All right, so first, put the coefficient matrix in row echelon form. We multiply row 1 by -1/3, so that gives us 1, -4, 2 in the first row. Then we need to take row 1 times -1, add it to row 2, replace row 2, so that gives us 0, 2, 0 in row 2. Now we need to change that 2 to a 1, so we multiply row 2 by 1/2. That gives us 0, 1, 0 in that row 2. Finally, we'll take negative row 2 added to row 3 and replace row 3, and that gives us 0, 1, 0, 1 for our final row. So this is a row echelon form of the matrix. So we use that as our upper triangular matrix. And again, it's just a style that we're using to get ones down the diagonal. We don't absolutely have to have ones down the diagonal for either L or for U, but Usually we'll get the ones down the diagonal for u just because it makes that system a little bit easier to solve. We don't have any divisions to compute there. We've already taken care of the divisions in the row, putting it in row echelon form. All right, so the row echelon form is our upper triangular. The lower triangular is to look at the inverse of each of the row operations and multiply them together in the order that we did them. Since we're doing the inverse of them, it's just like when we did the product of the matrix as, when we wrote the matrix as a product of elementary matrices, we do the inverse of each of them. And remember that when we do the inverses, it reverses the order of the product. All right, so to undo a negative 1/3 times row 1, we multiply by negative 3. To undo negative row 1 added to row 2, we just take row 1 added to row 2. To undo a half of row 2, we multiply row 2 by 2. To undo negative row 2 plus row 3, we add row 2 and row 3. And we multiply those four matrices together, and we get negative 3, 0, 0, 1, 2, 0, and 0, 0, 1 as our lower triangular matrix. And again, if you take the lower times the upper, you should get the matrix that you started with. So if you take this L and multiply it by this U, you should get the matrix that we started with. All right, so for the first step is to solve the lower triangular system. So we don't use x, y, or x1, x2, x3 here because we're replacing the upper times the variables with just a set of variables, so call them something different. I called them A, B, C. The previous examples, we called them U, V. The letters don't matter, just don't use the letters that we're trying to end up with. The first row gives us negative 3a equals negative 33. Tells us a is 11. The second row tells us a plus 2b equals 7. Solve for b using that value of a gives us 11. The third row tells us b plus c is negative 1. Plug in the b value, we get c is equal to 1. So 11, negative 2, 1 are the values for the variables that solve the lower triangular system. We use those now as our constants and solve the corresponding upper triangular system. The last row gives us x3 equals 1. X2 gives us, the second row gives us x2 equals negative 2. The first row gives us x1 minus 4x2 plus 2x3 is 11. Plugging in what we found for x3 and x2, we get x1 is 1. So we finally get here that our solution is x1, x2, x3 equals 1, negative 2, 1. So again, here, after we found our lower and upper triangular, we solved the lower triangular system using what's typically referred to as forward substitution because we're working from row 1 to row 2 to row 3. Got an intermediate solution, used that to find our final solution using back substitution. And again, back substitution says that we're going from row 3 to row 2 to row 1. Hopefully this helps a little bit with understanding how LU decomposition works for solving a system of equations.